Thank you for the invitation. Good afternoon to all of you. So I'm here to present this work about the submarine morphology of Madeira Archipelago. So basically what we did here was just look at the morphology of the submarine part of the archipelago and try to infer the process that gave rise to that morphology. So I was trying to show where Madeira Archipelago is. So Madeira Archipelago is here. You can see my mouse. So it's located around 1,000 kilometers southeast of Iberia, and it is formed by 4 islands, and one of them is Selvagens, is very near the Canaries. I will not speak about that island. I will speak about these 2, which are very near each other. So Madeira is the biggest island. So it's a very tall island, almost 2,000 meters and about 741 square kilometers. It has volcanism since 7 million years old until the Holocene, so it is very recent volcanism. And it has a very well developed subaerial drainage, as you can see here on this image. And it has a very high precipitation. It can reach up to 3,400 millimeters per year. So desertas are these islands here. They are very small. They are now extinct about 1.9 million years ago. So they are very low and small islands. As I said, they only reach not more than 477 meters height, and they are very small, so they only reach 14 square kilometers, and they have no subaerial drainage at all. And then Porto Santo, which is this island here on the upper left side, which is a very old island. It has been extinct since 10 million years old. It is also a very low island, which around 500 meters height and medium size, 42 square kilometers. It has a very small subaerial drainage and very low precipitation in comparing to Madeira, so less than 400 millimeters per year. Okay, so basically until very recently, we didn't know nothing about the submarine morphology of Madeira Archipelago because we relied on geobathymetry, which, as you can see in this image, you couldn't see very much. So we decided to make a compilation of all the multi-beam bathymetry and single beam bathymetry that we had in the archipelago. And this is a slide that shows all the data set that we use. So I'm not going through it in detail. So but basically just to say that everything is multi-beam with the exception of the orange parts. So the orange part is single beam bathymetry. It is also available on MONet. And so with all this, we made this compilation of all the bathymetries available and reached to this grid. This is the grid that resulted from this compilation. As you can see, we don't see much here nor here because this is basically based on single beam bathymetry. But as you can see, the rest is very visible. The morphology of the flanks and deep slopes of the island. So we basically, looking to this, we saw 4 types of morphologies, mainly erosional, gravitational, and sedimentary morphologies. So we found out that there were a lot of flank collapses and their respective debris avalanches. We also found out a series of gullies and canyons, as you can see here, a lot of canyons. Scours, which are these features here that I will talk more in detail, and also deep sediment wave fields that you can see somewhere here. Although with this zoom, it's not really possible to see much now, but I'll show that in more detail. So we were able to identify 7 main flank collapses. And how did we identify them? We basically, most of them have a amphitheater shaped or concave shaped scar on the shelf edge, as you can see, most of them, with the exception of this one. And they also have similar morphology on the subaerial edifice, like you can see here. So they also have a very well-developed lobe-shaped debris avalanches, as you can see here, or this one. And some of those debris avalanches have really big isolatic and irregular rocky outcrops, which are blocks that derived from these flank collapses. And the biggest ones have around 3 by 3 kilometers of size. So these are really big blocks derived from these collapses. So about their age, we didn't know much about it. We just tried to infer it based on the morphology that we see. So this is a slide of desertas islands, and we see that are channels already, I mean, canyons already developed over the debris avalanche deposits. And we also see that the Submarine island has a similar shape as the shelf edge scar, which means that probably most likely the Submarine island reached the shelf edge. So before erosion, this was the island. And then when the collapse happened, it happened where the island was here. So which means that you already have a very wide shelf, around 2 to 3 kilometers wide, that has developed after the collapse. We also look, here is an example from Madeira Island. This is the northwest part of Madeira. This is a very big, one of the biggest collapses. And you can see also that Submarine Island has the same morphology, so which means that before the collapse, the island reached the shelf edge. So the island was up here before erosion. So here, similarly, we have already a 2 to 3 kilometer wide shelf, which means that some time has gone since the collapse. And you also have a series of lava deltas. Some of them are dated, and one of them, it's this São Vicente lava delta, which does not exist anymore on the shelf because it was mostly eroded by wave erosion. But we have a date, so we can see it on the stream, and we have a date of 910,000 years old. So it means that most likely this collapse is older than this. So probably all these collapses, given the wider shelves and some of these datings, show that they are probably older than 1 million years old. So in terms of sizes, I calculated the areas of the debris avalanches and compared them with very known 2 other archipelagos, the Canary and the Y, because they are probably the best known studied archipelagos in the world, and they have recorded also a lot of flank collapses and their debris avalanches. So here on this table, we can see the sizes of the areas of the debris avalanches, and you can see that the biggest one is from the southeast Madeira, which is this one, and it has around 4,000 square kilometers. And we can see that the biggest one in the Canary is Puerto Rosario in Fuerteventura, which is more or less the similar size. And in Hawaii, we have very 3 big ones, between 13 and 26,000 square kilometers, but all the other ones have similar sizes to the Madeira ones. So this means that, well, all of these flank collapses that you see in Madeira and Desertas and Porto Santo are of similar sizes than the ones mapped in the Canary and the Hawaii. So changing a bit the subject, we are going to now look to the system of the submarine drainage of the flanks of these islands. So we have mapped a system of gullies. So the gullies are these blue ones here, and canyons, which are the black ones. So as you can see, the canyon system is very well developed north and south of Madeira. Actually, you cannot see the development of to the southwest because this is single beam bathymetry, but probably this system of canyons will develop further south. So they can reach around 7 kilometers on the north. Probably they can reach more on the south, but you don't know. And in areas where we have a lot of debris avalanches, the canyons are not so well developed because probably this is very rocky and hard to incise. Okay, so the gullies, they are these blue ones, as I said. They occur normally below the shelf edge in very high slope areas, so 20 to 30 degrees of slope. They normally have a V-shaped profile in cross section and can be 5 to 10 kilometers long, and they can have some hundreds of meters wide. These gullies are mostly dendritic, and they converge into the canyons, and as you can see here in some examples. The canyons occur at the deeper parts of the slope. Normally, gradients below 15 degrees, they have normally a U-shaped profile in cross section, and they can be 500 meters to 5 kilometers wide, such as this one or that one. And as I said before, they can reach 70 kilometers length, although here I suppose they will reach much more. Well, similar to gullies, the canyons also have dendritic shapes, as you can see here, that converge into a bigger canyon. And well, both the gullies and the canyons, they are responsible for transporting sediments from the shelf to the deep sea. So the idea here was what are the source of these gravitic flows that from the canyons, which process is triggering these gravitic flows. So as we know from the literature, Madeira, Madeira, big island, it has a very well developed subaerial system drainage. And as I said before, it rains very, very much. So it reaches around 3,000 something millimeters per year. So we know that in these settings, rivers or streams, in this case, Madeira has no rivers, but has big streams, very well developed. They tend to form what is called hyperpigmental flows. Okay, so these are flows that have a very high concentration of suspended sediments. And when they reach the sea, since they have a very high density compared to the sea, they normally plunge. And since we have a shelf with 2 or 3 degrees of gradient, these flows continue as a turbidity currents by the action of gravity. So when they reach the shelf edge, they normally accelerate on the slope. And because the slope here reaches around 20 to 30 degrees, so they start really incising the slope and they start forming the gullies. For instance, we have an event that it was the flash flood of the 20th of February 2010. Probably some of you have heard about it, where it rained around 500 millimeters in around 24 hours. So with that event, that flash flood delivered around 220,000 cubic meters of sediments to the Funchal, which is the capital of Madeira. And you can see an image of the harbor in Funchal and how it became. And historically, we have examples of a lot of flash floods occurring in the past. So 8 in the 19th century, 22 in the 20th century, and already 2, including this, the 2010, in the 21st century. So these prove that probably are the triggering mechanism of the turbidity currents in the canyons are probably these hyperpigmental flows. I can show you here an example. This is one of the biggest streams in Madeira, and you can see the debris that leaves from the deposition of these flash floods. Just for your knowledge, some of these blocks that you see here are around 50 meters of size. Another way of transporting sediments offshore is offshore transport of sediments during storms. This is a sketch that tries to show that. So here in brown we have a cliff and then a shelf. So this represents the shelf, and this point here represents the shelf edge. So what this shows is that when you have very big storm surges that are quite often normal in Madeira, especially in the northern part of the island, they produce what is called high pressure gradients, which is basically a storm coastal setup. And because we have a cliff, so this water that is pushed against the cliff needs to be balanced by offshore directed ebb currents. So these ebb currents, or could call also downwelling currents, they normally what they do is to transport the sediments that are near shore to the offshore. So during the storm, sediments that are near shore are easily entrained and maintained in suspension by the waves and by the currents. And then the combination of the high excess weight of the suspended sediments, I mean the gravity, and the relatively high gradient of the shelf, like 2-3 degrees, and this current, this strong ebb current, transports sediments from the near shore to the offshore. Well, some of them are deposited on the offshore part of the shelf, forming clinoform deposits, but others probably they cross the shelf edge and they reach the slope, and they probably aid to incise the gullies and the canyons. Well, I have here this a sketch of a paper that I like very much. This is a work that these authors have done with an analogic experience. Well, what they did is just created a shelf, which is this part here, and then the slope made of sand, and they starting to intrude some and confine gravity flow, a saline flow from the coastline, which is represented here, to the shelf edge. So since the shelf has a slope, so this unconfined flow just goes down the slope, and when it reaches the shelf edge, it starts increasing its speed, and it starts incising the shelf by small gullies that develop to bigger gullies, and they start forming canyons, as you can see here, and also airward erosion of the shelf edge. So basically, if you think of these flows could either be hyperpigmental flows from the streams of Madeira, or could be, I mean, storm flows transporting sediments offshore, and they will do the same that we see here on this example. We have here some examples of Madeira. This is the southwest part of Madeira, and we can see here two well-developed canyons that are having headward erosion, and probably these flows are, some of them are promoted by the streams, others they could be by storm processes. Either way, they will be responsible for canyon development. So in Madeira, which is a very big island, it has a very high subaerial drainage. Probably what is forming the canyons, I mean, the flows of the canyons are associated with the hyperpigmental currents from the streams. In Porto Santo, that we don't have any subaerial drainage very well developed. Well, in the Zetas there is no subaerial drainage at all. Probably what is forming these flows that reach the slope are the storms that are supporting sediments offshore. Okay, so passing for different subjects, we now will look at the scours and the sediment wave fields that we see on Madeira. In black we have mapped the scours, and in red we have the sedimentary wave fields. So the scours are basically big scours that we see on the lower slopes, and they are probably not formed by a single event, by a landslide, but probably by continuous flow erosion. Both the scours and the sediment wave fields are normally where there are no canyons, so they're normally outside the canyons. There are some sediment wave fields that are inside the canyons, but normally most of them, both the sedimentary wave fields and the scours, are outside the canyons. So the scours, and we have here an example here, they can be 10 to 50 kilometers wide, 20 kilometers length, and around 200 meters deep. So as I said, they normally occur isolated, as in this case, or normally upstream of the first sediment wave fields. Both of these features occur between the 3,000 and 4,000 meters depth, and where the gradients of the slope of the island decrease to 3 degrees. The sediment wave fields, this is one of the biggest examples that we have here. These wave fields, they have wavelengths of 600 to 5,000 meters length, and wave heights of 2 to 100 meters. As I said before, they normally occur downstream the scours, and where there's the canyons end. So you don't see it very well here, but we'll see in the next image. The canyons normally end at about here in desertas, and some of them also occur in the lobes of the debris avalanches and inside the canyons, as this example here. So as I said before, these scours and waves, they occur mostly in unconfined part of the island, so where there are no canyons. We have here examples. So this is a cross-shot profile showing where the scours start to develop around here, the scours, and then the sediment wave fields. So you can see here in the cross-shot profile. So you have very big gradients of 20-30 degrees in just immediately below the shelf edge. So this is the shelf. This is the shelf edge. And then when the gradients start to decrease to 2-3 degrees, we normally have a big scour, and then the sediment wave fields. Well, the ones with the highest wave heights, and then some smaller waves that have smaller heights but have a wider wavelength. Okay, so this was the animation. So you can see here are the scours and the sediment wave fields, and some of them are inside the debris avalanche deposits, as you can see here, but others there aren't. So we think that some of these wave fields are compressional features from the placement of the debris avalanche deposits, but the ones that are outside, we don't think so. We think they result from hydraulic jumps formed by these turbidity currents that we saw that are draining the slopes of the island. So for those who don't know what are hydraulic jumps, I have here a sketch to try to explain very briefly. So a hydraulic jump occurs in a channel, but not only in channels, when very high velocity supercritical or turbulent flows meet slower moving subcritical or laminar flows of water. So this is an example here. So this transition between supercritical and subcritical will create a turbulent flow in the middle. So we have here, for instance, try to imagine this as the shelf, and here the slope. And when the gradients decrease from the slope to the deep sea, there is a transition from the turbulent to the laminar flow, and creates this turbulent area where normally there is erosion, and further offshore there is deposition. So that's what we think that is it's forming here the scours and then the sediment wave fields. As you can see here from this sketch, it's exactly in the area where there's a big gradient decrease that starts forming first the scours and then the sediment wave fields. Well, this is mostly already known in continental margins and in the turbidite systems, what is called a channel lobe transition zone. So the channel lobe transition zone is a zone where the canyons normally end. So we have confined flows, turbiditic flows from the canyons, and normally where the canyons end, there is a break-in slope, which is represented here in a cross-shot profile, here in plan view. And normally in this channel lobe transition, we have first a lot of scours and then the sediment wave fields. So this is very well known from most continental margins. And I think this is the same that is happening here in Madeira Island. So in conclusion, so below the -300 meters, so it takes place the first hydraulic jump with a great erosive power, forming the scours, one or more scours, and then the subsequent hydraulic jumps have less erosive power and they form the sediment fields. So nevertheless, some wave fields might result from the compressible features associated to the emplacement of the debris avalanche deposits, and of course there are also some wave fields that are inside the canyons that are also formed by these hydraulic jumps, where there is a big gradient decrease. In conclusions, I just want to stress that we have mapped some very large flank collapses that destroyed significant parts of the submarine edifices, and probably occur in the early stage of the island building, for sure older than 1 million years old. We also have mapped a turbidity system that is really well developed in the taller and rainy islands, such as Madeira. In the case of Madeira, this turbidity system is probably triggered by hyperpigmental currents. And in the case of the smaller islands of Porto Santo and Desertas, this is triggered by the sediment transport during storms. In the low-lying and dry islands such as Porto Santo and Desertas, the turbiditic systems are very poorly developed. So we mostly have very small canyons that unconfined very easily in the deeper parts, and they favor the development of scours and sedimentary fields. And also in the parts of Madeira that they don't have the canyon system, we can also see the scours, and in some cases also some smaller sedimentary fields. And basically that's it, what I want to present. I've posted here also two papers that I published very recent. One about this work that I've shown here on the left side, and on the right side it's a paper about the Selvagens Islands, which are also from Madeira Archipelago, but they are much further south, very near the Canary Islands, and which shows exactly the same type of morphology and the same type of processes that are driving the submarine morphology. And I want to thank you for your attention.